Take a moment to look around you. The desks, the walls, and the chair you're sitting on. If all these things are made of individual atoms, then why doesn't everything fall apart? What holds the atoms together? The answer is chemical bonds, which help form everything around us. In this video, we'll explore the concept of bonds, and we hope you'll learn some valuable information that will aid you in the future. Let's begin with a simple question. What exactly is a chemical bond? In chemistry, a bond is a lasting attraction between two or more atoms or ions that enables molecules and other structures to form. They are the forces that hold hydrogen and oxygen atoms together in a compound such as water, or the forces that bind atoms together in perbromic acid, which for some reason looks like this. Without them, we wouldn't have molecules, and the world we know today would not exist. Bonding processes require the transfer or sharing of electrons, and the atoms typically form bonds in order to reach a more stable, lower energy state. In some cases, this involves the complete transfer of an electron from one atom to another, forming what is known as an ionic bond. Other times, an electron is shared between atoms, resulting in a covalent bond. Another type is a metallic bond, in which atoms are held together in a metallic substance. These types of bonds form the basis of many chemical reactions and are an essential aspect of chemistry. We will talk more about these types of bonds individually throughout the remainder of this video. Let's discuss ionic bonds first. An ionic bond, otherwise known as an electrovalent bond, is a type of chemical bond in which electrons are not shared, and instead the cation completely gives up one or more electrons to the anion. As a result, this forms an ionic solid, which is held together by a strong electrostatic attractions between the ions within a lattice structure. Ionic bonds often occur between metals and nonmetals, and the ions within them typically have vastly different electronegativity values. A prime example of an ionic solid is sodium chloride, which is commonly known as table salt. Sodium chloride exhibits very strong electrostatic forces between its ions, which accounts for why it is solid at room temperature and has very high melting and boiling point. This is also the case for most other ionic solids, and two primary factors are responsible for these high melting and boiling points, which is explained by Coulomb's law. The first factor is the charge of the ions, since Coulomb's law states that a greater charge leads to greater bond energy. This can be observed when comparing magnesium oxide MgO and sodium fluoride NaF. This is because magnesium and oxygen atoms have greater charges than sodium and fluorine atoms, making magnesium oxide significantly stronger. The second factor is the relative size of the ions, since smaller ions will have greater Coulombic attractions. Thus, a substance such as lithium fluoride would have greater attractions than potassium bromide. That's enough for ionic solids for now, though. As Mr. Mack would say, now is a great time for a clever chemistry joke. Two atoms are walking together, and one says, "I'm positive I lost an electron bumping into that anode." The other responds, "Well, isn't that ionic?" Get it? Ionic instead of ironic? Okay, we're sorry. But if you did laugh at that, though, you have a very broken sense of humor, and I'm deeply concerned about your sanity. In addition to ionic bonds, there are also metallic bonds. Guess what type of compound exhibits metallic bonds? That's right, metals. Here's your star. As you can see, chemists are very original. In metallic bonding, the positively charged core of a metal, which consists of its core electrons and its nucleus, is usually stationary, whereas the valence electrons are usually delocalized and very mobile, moving from one atom to another. This explains why metals are excellent conductors of electricity, as well as why metals are malleable and ductile. Metallic bonding is especially common in minerals involving transition metals, such as gold, silver, and copper. Metals also bond with each other to form alloys, which are combinations designed to increase strength and hardness while retaining the original properties of the metals themselves. There are two fundamental categories of alloys as well: interstitial alloys and substitutional alloys. In an interstitial alloy, metal atoms with two significantly different atomic radii combine. An example of this is steel, which consists of smaller carbon atoms between larger iron atoms. In its substitutional alloys, metal atoms with similar size radii combine, such as in brass. In brass, atoms of zinc are substituted for some copper atoms, forming the alloy substance. Let's move on to covalent bonding. In a covalent bond, electrons are shared between atoms, and each atom counts these shared electrons as part of its valence shell. Covalent bonds occur between non-metal atoms, and when two or more of these atoms bond through the sharing of electrons, a molecule is created. There are also two types of covalent bonds: polar covalent bonds, where the electrons are unequally shared, and non-polar covalent bonds, where the electrons are equally shared. An example of a non-polar covalent bond can be found in the compound N2, nitrogen gas, because the bonded elements are identical and therefore share electrons equally. An example of a polar covalent bond is in the compound carbon monoxide. Since oxygen has a higher electronegativity than carbon, the shared electrons will be more attracted to the oxygen atom. There are also different designations of covalent bonds. Sigma bonds are the strongest and the first covalent bonds to form. Pi bonds are weaker and formed afterward for double and triple bonds. In addition, covalent bonds have different lengths, which depend on a balance of the amount of repulsive and attractive forces between atoms. This can be modeled by observing hydrogen gas, since a bond forms at the lowest potential energy level. When they're too close to each other, potential energy is too high due to repulsion between nuclei. When the atoms are too far from one another, potential energy is close to zero, with very little attraction. There are also network covalent solids, in which atoms are held together in a lattice of covalent bonds. These network covalent solids have high melting and boiling points, yet they are poor conductors of electricity because they do not have any mobile electrons within them. Most network covalent solids contain carbon, such as diamond and graphite, or silicon, such as quartz and glass. Congratulations, you made it to the end of the video. We hope you learned something new today, or at least got to refresh your memory about the different types of bonds and their characteristics. Thank you so much for watching and have a nice day. Congratulations, you made it to the end of the video. We hope you learned something new today, or at least got to refresh your memory about different types of bonds and their characteristics. Thank you so much. I hate you. I hate you.
Please, David.